Check it out now, y'all.
nanoHUB-U, online instruction.
Okay, welcome to Fundamentals of Nanotransistors. I'm Mark Lundstrom, and this is Lecture 1 of Unit 1. What I want to do in this lecture is to tell you just a little bit about what the course itself is about, and then in a little bit more detail what we'll be doing in Unit 1. So this is a course about transistors. Here's a cross-sectional transmission electron micrograph of a silicon MOSFET. And you can see the basic components. It's very descriptive. There is a terminal here labeled source. That's the source of electrons. There's a terminal here labeled drain. That's where the electrons go out of the device. And there's a gap in between, and there's an electrode labeled G for gate. That controls the flow of electrons from the source to the drain. It's built on a silicon wafer. There's a silicon substrate that goes down very deeply here. And this is the basic device that we're going to be talking about. Now, if we look at the heart of the device, blow up the active part right in the middle, you can look in a little more detail. We see the gate electrode. We see a very thin insulating glass layer, 1.1 nanometers thick today. That's half the diameter of a DNA double helix. So these devices have become incredibly small. If you look at this gap between the source and the drain, the channel, that's in current day technology, that gap is about 20 nanometers. Again, less than 10 DNA double helixes stacked side by side. So the dimensions of these devices are very, very small. In the 1960s, when MOSFETs like this were first built, the channel length was on the order of 10,000 nanometers. Today, 10 nanometer transistor technology is under development. That's a factor of 1,000 reduction in the length of the channel, a factor of 1 million reduction in the area of the transistor. It means that we've been able now to put 1 million times more transistors on the same area of a piece of silicon, and that's what's driven progress in electronics for the past 60 plus years. Okay, now we're going to be talking about transistors. Sometimes when I'm drawing circuits, I don't want to draw the entire physical structure. I'll use this circuit symbol. And there you can see how we're labeling the source, the drain, and the gate. Now, we can use transistors in two different ways. We can use them as digital devices. So we can think of them as a switch, and the switch is either open or closed. So there's either a 1 or a 0. That's the basis of digital electronics. Now, we could use the transistor in a different mode. We could amplify things like my speech or music. And in that case, we would be amplifying a small signal, maybe an AC signal that we put in the gate, and we would be getting a large signal out. The device would act as an analog amplifier. That's the basis of analog electronics. So we'll be talking mostly about the use of transistors, mostly about the physics of transistors, but mostly about the use of them in digital circuits and just a little bit in analog. Now, modern MOSFETs have evolved over the last 60 plus years to become very sophisticated. So this cross-section is a very good illustration of what a transistor is and what the key components are. It's about 15-year-old technology right now. These days, there's some more advanced technologies that companies are using. So for example, one of them is called silicon on insulator technology. And you can see here the active layer of the device, the source, the channel, and the drain, all of that sits on an insulating layer of glass or silicon dioxide, and then it sits on a thick silicon wafer. The function of the silicon wafer in this device is just to hold everything up. And this device has some advantages when we scale devices down to very small dimensions and reduce capacitance and things like that. It's called an extremely thin silicon on insulator MOSFET. Now here's another even more sophisticated device. This is a FinFET. So this is the technology that Intel is developing these days. And you can see that what's produced is a tall fin of single crystal silicon. And the source and the drain are on the two ends of that fin. And then the gate electrode is wrapped around that fin. So this has some advantages. We'll talk about what the advantages are later on in the course. It's much more sophisticated. You can see in this cross-section electron micrograph of what a couple of those fins actually looks like. So this is a course really not about the details of the fabrication of structures like this. The basic principles of operations of these transistors are all pretty much the same. We will talk from time to time about why people are going to these sophisticated structures, but we'll really keep the concepts very generic, and they'll apply generally to transistors. We will mostly be talking about silicon transistors, but we will also talk a little bit about another class of transistors made of different types of semiconductors, 3-5 semiconductors, materials like indium arsenide, gallium arsenide, and these transistors go by a couple of different names. They're frequently called HEMTs, for high electron mobility transistors. The distinguishing feature of these materials is they're very high electron mobilities. And you can see that the device structure of a typical 3-5 HEMT is much different from a silicon MOSFET, but there's a source, there's a drain, there's a gate, and it really functions under the same basic physical operating principles. So we'll talk about this device a little bit also. Now, the objectives of the course are very simple. There are two main objectives of this course. So the first is to understand the physical operation of these transistors that have become very, very small. So we want to understand the physical operation, how electrons flow from the source across this incredibly short channel and out the drain. And then we want to relate the physical operation of that electron flow to the current voltage characteristics. And these are typical current voltage characteristics of transistors. We want to understand a little bit about why they're useful in building circuits, but then we want to understand how we relate these current voltage characteristics to the physics of what's going on inside the device. And that's really what the course is all about. So the course consists of 4 units. We're beginning Unit 1 right now. The first two units will be review and background for some of you. For those of you without a background in transistors, it will be new. So Unit 1 is some very basic fundamental concepts about transistors, just to get everybody calibrated, define some terms, and get everybody on the same page. Unit 2 is about MOS electrostatics. So this is all about how we control the electric fields and potentials inside the channel with the voltages that we put on the 3 terminals of the device. Now, this hasn't changed much in the 60+ years that transistors have evolved. The same principles still operate. It's much more difficult to control electrostatics properly in these incredibly short transistors, but the basic physics hasn't changed. Those of you who have had a course in semiconductor electronics and MOSFETs have probably learned this material in the traditional way that it's taught, and Units 1 and 2 will be a quick review for you. And for others, it'll just introduce you to some basic fundamental concepts that we need to understand transistors. Now, Units 3 and 4 are the really different part of the course. Units 3 and 4, we begin to talk about how modern-day nanotransistors actually operate. And this is material that hasn't yet made it into the textbooks. So this is what makes the course special. In Unit 3, we'll talk about the ballistic MOSFET. In the ballistic MOSFET, electrons go from the source to the drain without encountering any obstacles. They don't scatter off of anything. It's just like they were being shot out of a cannon and going through a vacuum, and they go very quickly across the channel. Unit 4, we introduced what we call the transmission theory. And this is the full way of understanding transistors at the nanoscale. Includes the fact that some of them are going to scatter off of lattice imperfections and lattice vibrations and things like that. And this will give us a very solid but simple fundamental understanding of how these incredibly small devices operate. Now, the prerequisite for this course, I'm going to assume that you have a basic understanding of semiconductor physics. The type of understanding that you would get maybe in an undergraduate course on modern physics, or if you've had a course, a beginning course at an undergraduate or beginning graduate level on semiconductor physics, that kind of understanding. If you have that basic understanding of semiconductor physics, you should be in good shape to follow the course. Now, in this particular unit, I can tell you a little bit more about what this particular unit is about. So we're doing the introduction right now. In the next lecture, I'm going to view the transistor as a black box. It's just something that has 3 or 4 terminals, and we're going to try to understand what happens when we apply voltages, what current flows. Now, we won't inquire what's inside the box. That's what the course is all about. In lecture 3 of this unit, we'll talk about some device metrics. There are some key device parameters that device designers look at. If you can achieve these metrics, then your circuit will perform well. And we'll define what those key metrics are. Now, this is a course about how the device operates, about the physics of the device, not about circuit design. But we need to understand a little bit about how device performance relates to circuit performance. So we'll do that in lecture 4. In lecture 5, I'm going to present a very simple view for how the transistors work. And it's a view that makes use of energy band diagrams. If you've had a course in semiconductor physics, you'll know what an energy band diagram is. And it gives a very intuitive and simple way to understand how these devices work. And once we have that understanding, then we can fill in the details for the rest of the course. Now, lecture 6, I'll quickly go over the traditional way that MOSFET theory is presented. The way we do it in a beginning undergraduate course and the way we do it in a beginning graduate course these days. So this is the way that was developed when transistors were first invented. Modern day transistors operate differently, and the traditional theory wouldn't seem to apply. So really what this course is about is how we understand, how we use concepts that are appropriate to the nanoscale to understand these very small devices. But we want to relate all of this to the traditional way that MOSFETs are taught and that people have thought about them. In lecture 7, I'll introduce something called a virtual source model. This is a very simple model of nanotransistors that turns out to work remarkably well. And we will use this as a framework throughout the course. We will present it in lecture 7, and then we'll come back to it repeatedly throughout the course and refine it and update it and understand how to interpret the various parameters in the model in a very physical and sound way. And then lecture 8 will just wrap up the basic concepts and make sure that everyone takes away from Unit 1 some of the key concepts you'll need to be successful in the rest of the course. So I would like to ask you, please ask questions. You know, we look forward very much to a discussion on the electronic forum. So ask us questions. If you don't do that, I really won't know where you're at and how we can. We're looking forward very much to it, having a dialogue with you. I want to point out that there are some additional resources, and you will find these from time to time in each unit. We'll point you to some resources on the web where you can get additional information. The one I want to point you to immediately is the quick review of semiconductor physics. So if you're not completely sure whether you have the background to be successful in this course, have a look at that lecture. It doesn't teach semiconductor physics. It presents material that I typically go over in 5 or 6 weeks when I teach an introductory semiconductor physics course. But we'll quickly go over the key concepts that you should be familiar with or that you might need to review in order to be successful in this course. And I'll also be providing to students in this course a set of draft lecture notes that will be published by World Scientific soon. So there's much more detail in those lecture notes than we'll do in the lectures. So again, please ask questions, and we look forward to interacting with you in this course. Thank you.